Okay, welcome everybody. So we've talked a little bit about percent yield in class, and so you should have an idea of what it is. But just to go through it again, quickly here for you, you have an actual yield, so what you would actually make in the lab, so this is your result, over the theoretical yield, times 100. And that would give you the percent yield for a reaction. Now these questions could be a little bit tricky because we could have a limiting reagent problem where we put that together with this. And so if I were to give you something like this, if I were to give you you know where you have a combustion reaction, something like methane plus oxygen yielding carbon dioxide and water, and I were to balance this and have my 2 and 2, so now I have my balanced reaction. So if I were to say something like you were to combine 32 grams of CH4, and you were to combine that with 32 grams of oxygen, and then I were to ask you, well, what would be the percent yield if in the lab the reaction produces and I would say, um, 22 grams of CO2. And so people get confused by this type of wording because they look at this and they're like, well, he already told me how much I make. So I can just add the 32 and 32. I get 64 grams. I do 22 over 30 over 64, and I'm done. And it turns out there's a lot more to it. In this problem, I've given you the actual yield down here. But you have a lot of work to do. In order to solve this problem, and we'll do that in red, in order to solve this problem, you have to find the theoretical yield. And so if I have 32 grams of methane, I picked that on purpose, that would give me 1 mole of this. Sorry, 2 moles of, thinking of oxygen. That will give me 2 moles of CH4. And if I convert this, that gives me 1 mole of O2. And so when I look at this, if I have 2 moles of CH4, I'm going to make possibly 2 moles of CO2. If I make 1 mole of O2, I'm going to only make a half a mole of CO2. Now if I make half a mole of CO2 and I convert that to grams times 44 grams, then that would give me a 22 gram theoretical yield. Now being an amazing chemist, and however I picked this number off the top of my head is crazy to me, but I have, if I were to plug this in, I have 22 grams from my actual yield, and that I got from here, over 22 grams from theoretical. And so in this case, miraculously, I have 100% yield. If I try this again and we do this in like a different color, like, ooh, I can move to this way now. That's awesome. They added more colors. It's exciting. So if I were to do it in green now, let's say that in the next situation, I would have only made 11 grams of CO2 in the lab. Well, my theoretical hasn't changed. My theoretical is based on the numbers that I reacted. So when I go and I try that one in green here, my new calculation would be 11 for the actual over my 22 grams for the theoretical, and times 100 there, so now we're down to a 50% yield. So be careful with this. If they give you a number that the product formed in the actual problem, that's the actual. You have to go and find the theoretical. And we could twist this problem. I could tell you, well, the percent yields 80%, and how much did you make? And so then you could figure that out. In fact, that's probably a good one to do on the side here. If you were to say, if I gave you the percent yield was 80%, how many grams of CO2 formed? So use all the numbers down here, the 32 grams, the 32 grams, and from there go and see if you could find that. We'll talk about it tomorrow. Okay, so now we're going to kind of take a step back, do a little bit of percent composition. Percent composition is easy for you. It's just part over whole times 100. So, here, if I give you a compound like barium nitrate, I give you barium nitrate, and I ask you, what's the percent of barium in there? So find the total mass. You go to the periodic table, you look up the total mass, use the mass of barium, which is 137, and then you plug it into the equation. 137 over 261 times 100 gives you the percentage. That should be easy for you. But then we could do something more advanced. I could give you something like, give you an impure sample, like a 50-gram sample of an ore. An ore is just basically like a nice rock. Contains minerals in it, contains compounds. So I say, hey, you got a 50-gram sample of this ore. It contains 23 grams of iron oxide, iron 3 oxide. What's going to be the percent of the iron in the ore? Well, for this, I got to do a little bit more work. So let me figure out how much iron I have. So first I start with my 23 grams of the compound. So now if I go here, let's do a different color. These new colors, I am just blown away. You're probably laughing at me, but I'm in love, man. That's amazing. Okay, so we have 23 grams of iron oxide. And I like to do this using moles. So I like to say, all right, well, times 1 mole for every, and I find the gram formula mass. I add it up. It's like 160, I believe. So I have the grams of the iron oxide. So now I cross out grams and grams. Now, this is 1 mole of Fe2O3. So for every 1 mole of Fe2O3, there's 2 moles of iron. And then I can change it back to grams. Well, there's, I think iron's 56 approximately, 55.85, but I'll make it 56 grams of iron for every 1 mole of iron. And this will give me my grams of my iron that are in the sample. And so if I do that on my calculator, I do that on my calculator and I get my 23 divided by 160. I times it by 2, and I times it by 56, and I get that there's 16.1 grams of iron. Rounded to 16 if we're using sig figs, and they want the percentage. So then I take that 16.1 and I divide it by 50 because that's the total mass of the sample, and I times it by 100. And I get about 32%. Is this problem really difficult? It's not crazy, but it's a little bit challenging, and I have some more that are kind of, plays on this same type of theme. But I like to do it with moles. Are there other ways to do it? Yeah, I'm sure you could think of other ways to do it. You could do multiple percentage compositions and get through that. But, for me, I keep it as moles, and I like that. Okay, the other thing is hydrates. So, with hydrates, if you forgot what they were, they're these compounds where you have something like a compound like copper sulfate. This one's really common because it's used in the lab a lot. And it has 5 waters. It's a pentahydrate. And so they'll show it with a little decimal there. But, here's a situation where I could use gram formula mass. So, the gram formula mass of copper sulfate, it's 160. Of the 5 waters, it's 90. If I wanted to find the percentage, I could do 90 over the total, which would add up to 250, times 100, and I would get about 36%. And that would be my 36% of water. You could figure this out on your own if you don't believe me, but I've done this problem like 100 times. I know it's 36%. So, what if I were to have it in the lab, though? So let's say you have some salt, and it's complexed with some, amount of water. And they don't tell you how much, and they don't even tell you what the salt is. And they don't have to. You do this experimentally. So you get this salt, it's solid, the water is actually, like within the crystals. And so let's say that this had a convenient mass of 10.0 grams. And then what you do is you heat it. And you did this lab last year where you had a blue solid, which was copper sulfate, and you heated it in a crucible, and then it turned to this gray color. And that was the process of the water being removed from the compound. And so you'll be left with just the salt in the, left over. And if you mass that, let's say that you get like, say you get 7 grams. And so the question would be, well, what's the percent of water in the hydrate? So you figure that out for me. Let's talk about it tomorrow. Should be able to do that fairly easy. There's a little bit of a twist to it, but it's nothing crazy. So the next thing that, if you know how to do percentages, you should be able to use those percentages to work backwards. If I give you a percentage, you should be able to find the formula, empirical and molecular formula of a compound. And so how does that look? Well, here's my compound that I'm going to do. I give you 75% carbon and 25% hydrogen. And a lot of people look at this and they're like, it's CH3, because there's 3 times, or it's HC3, something like that, because they look at it and they're like, 75% carbon, that's 3 times the amount of hydrogen. You can't do that. You have to get it into moles. So we assume a 100-gram sample. We convert the percentage to grams. So here we would have, if we assume 100 grams, 25 grams, and 75 grams. If they give you grams of the sample, you don't have to worry about being in percentage. Some people like to convert back to percentage. That's extra work. If they give you grams, go with it. So you convert the grams to moles. So we would take the 25 grams, we convert it to moles. That would be of hydrogen, and so we'd have 25 moles of hydrogen. We take the 75 grams of carbon. This time we're going to divide it by 12 for the gram formula mass, and we'll get 6.25 moles of carbon. Now, like at this point, really, I have a formula here. I have C 6.25, and I have H 25. But remember, to be an empirical formula, you need to be the lowest whole number ratio. Okay, so you need the lowest whole number ratio. So I need to divide these out. So I divide them by the smallest number of moles for each of them to get the ratio that's a whole number. If I divide them both by 6.25, I get that I have 4 hydrogens and I have 1 carbon and I have CH4. And we could take this a step further because this is an empirical formula. This is the lowest whole number ratio. This gives us some information, but not a lot. It doesn't tell us the true formula. If I give you an empirical formula, something like CH3 though, and I give you the true mass, the molecular mass as being 30, well, if I find the empirical mass, which is 15, I can compare it to the molecular mass. If I divide them out, I'll get 2. 30 divided by 15 is 2. So what that means is that, I then have twice as much of the elements. So instead of CH3, I multiply it by a factor of 2. I would get C2H6. So hey, try one of these. Let's say that you have, a sample that has, just do one here, do another carbon-hydrogen one. So let's say you have one that has, 92.3% carbon, and the remainder is hydrogen. So that would be what? That would be 7.7% hydrogen. So tell me what the empirical is. And then let's say that you had, a true mass. So in a separate problem, you have a true mass of 78 grams per mole. So tell me what the molecular formula is. And then impress me, name it, and see if you know what that is. Some of you might know what it is based on some of the organic chemistry that you've done. Now, what I want to do is, along the lines of empirical formulas, I want to talk about one more problem because this video is getting really long, and I want to do one more with you. So I'm going to come back to this slide on the types of chemical reactions. We'll do that on the next one. And I want to try this one right here. So pause the video, take a moment to write this down. This one's an advanced problem. It's a combustion analysis of a sample. It only contains carbon, hydrogen, and oxygen. I give you the mass of the sample, and then I tell you how much product you form, how much CO2, how much H2O you form. So I'm going to go through this quickly. So if you haven't seen one of these before, you might want to take the time to, like slow down and do it, and we'll do some more in class too. But what I like to do first is, I like to write out the reaction. So I like to say, all right, well, I have carbon, hydrogen, and oxygen. I don't know. I can do X, Y, and Z. And they're reacting with oxygen. They're combusting. And it's going to produce CO2 and H2O. And I can't balance this, and that's fine. Can't balance it because I don't know what X, Y, and Z are. So I need to figure that out. That's the point of this, finding out the empirical formula. So first I start with the products. And it's actually a student who, I did a little bit differently, but a student was like, why don't you just do this? It was a few years ago, and I'm like, that's a great idea. And since then I've been doing it this way. So what I first do is I look at the carbon dioxide. Look, all the carbon in carbon dioxide had come from this carbon over here. That's where it came from. The carbon is there, it went all into carbon dioxide. So I have my 1.900 grams of CO2. And now I'm going to see how many grams of carbon that would be. So in CO2, 12 grams are carbon for every 44 grams that are CO2. I'm just using the gram formula masses. When I do this, this tells me if I do 1.9 times 12 divided by 44, I will get 0.5181. And that's grams of carbon. Let me insert a page here in case I go over. So now, if I were to go and I were to do this again with water, well, they're telling me that I have 1.070 grams of water times, well, there's 2 grams of H for every 18 grams of water, or 1 to 9. So if I do this, I do my 1.070 divided by 9, I would get that there is 0.1189 grams of hydrogen. Now, I used to go straight to moles, but the reason why I don't, the reason why I stop here is because I know that in my compound contains C, H, and O. Well, the total compound, I'm told in the problem up top here, weighs 0.9835 grams. 0.9835 grams. That's equal to the carbon, which is 0.5181 grams, plus the hydrogen, 0.1189 grams of hydrogen, plus the oxygen. I don't know the oxygen. Well, now I can solve for it really easy. So plus the oxygen. So if I add these two, if I do, or if I just do 0.9835 minus 0.5181 minus 0.1189, I will get that my amount of oxygen that I have is 0.3465 grams of oxygen. Well, look, I have the grams of each thing. Don't change them to percentages, just change them to moles. Times 1 mole for every 12 grams, times 1 mole for every 1 gram, times 1 mole for every 16 grams. And let's go through and do it. We'll start with the oxygen. I got it on the calculator, divided by 16. So I have 0.0217, or 66 moles of oxygen. My hydrogen is going to be the same, 0.1189 moles of hydrogen. And my carbon's going to be the same. No, it's not. 0.5181 divided by 12. And I'm going to get 0.04318 moles of carbon. Well, I look for the smallest one, it's the oxygen. I divide them all out by that. We'll start with the carbon, since again I have it up on the screen, 0.02166. That gives me 2 carbons, C2. I do my hydrogens, 0.1189 divided by 0.02166. That gives me 5.5. Can't round that, unfortunately, to 6. And then I do my oxygens, I have 1. So my final formula would be C4, H11O2. That's my empirical formula. Look through this problem a few times. When we come in tomorrow, we'll start with this. A lot of you know the other parts. That was a review for you. This should be new. I don't think any of you have done a combustion analysis. Hopefully this was helpful enough for you to be able to recreate it tomorrow. Alright, thanks so much, and I'll see you soon.